Okay, assignment 1222. You guys should have tried these already. Just a couple more practice with differential equations, slope fields, and related rates. But overall, we're getting the hang of it. You can watch this if you have any trouble. See where the points go. So the points are going to be 2, 1, and 6. First point says on the axis provided, sketch slope field for the given differential equation at 12 points. Make sure you do 12, not less, not more. There might be some dots missing some places on the axis where it's hard to tell. It looks like there aren't 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I usually like to look for the zero slopes first, which are going to happen when x equals 0. So that's all of these. You just got a third of them. And also when y equals 2, there's going to be these guys. So we just took care of half the slopes. Might also be some symmetry about these. That'll help you speed up or see if you're wrong or whatever. We plug x equals 1 in, y equals 0. It's going to be negative 2. So down 2 over 1. If we do 1, 1, we get negative 1. So that's a little less steep. Up here, if we do 1, 3, we get positive 1. So kind of some symmetry there. If we do negative 1, 0, so negative 1 for x gets raised to the fourth as positive. So that's going to be negative 2. So like that. And then at negative 1, 1, we're going to get negative 1. And then at negative 1, 3, we're going to be at positive 1. So points-wise, 1 for all the zero slopes and 1 for all the non-zero slopes. If you mess one up, you lose that point. Part B says, while slope field in part A is drawn at only 12 points, it is defined in every point in the xy plane. It goes out forever. Describe all the points in the xy plane for which slopes are negative. Now, you might look at this picture and be like, oh, there's some negative ones, there's some negative ones, and maybe try and guess what's going on as it goes out further. But I think the more dependable way, and not very difficult, is to set the derivative to negative and solve it. So here, this is always positive, right? Except when it's 0, then the whole thing's 0. So this is the thing that we need to make sure is negative. So we could solve it. So y has to be less than 2, but x cannot equal 0. So that's one way you could describe it. Or you could say at points below y equals 2, but not on the y-axis. That's another way of describing the same thing. So that's just one point. But the bulk of the points are solving the differential equation. Find the particular solution for the differential equation given the initial condition of 0, 0. So this is where we're going to solve the differential equation. Now, you guys should, I don't know, I kind of feel like these are pretty predictable step-by-step problems. And so I kind of feel like they're kind of easy points. Just got to be careful. You got to separate the variables with multiplication and division. If you don't do this, this is worth 1 point. But if you don't do it, you just lost 6 points. Got to integrate both sides. Natural log the absolute value of y minus 2 equals x to the 5th over 5 plus c. So you got 1 point for each antiderivative, sometimes just 1 point total. You got 1 point for putting plus c. If you don't put the plus c, you lose the 3 points. Let's find the c value right now by plugging in the xy coordinate pair. We know the initial condition. And so then c equals natural log of 2. So that's another point. We plug it back in to the original equation. Everything else should still be there. And now we go solve for y, which is probably the most work, but the least calculus kind of work. It's just algebra. You need to exponentiate both sides. Now, rules of exponents say that you can break this up, which would lead to a nice cleaner version by making the bases the same, breaking up the base, and multiplication. You can't distribute it. To get rid of the absolute value, you got to do plus or minus. Now this is just going to be 2 e to the x to the 5th over 5. Now we should choose plus or minus. Do not leave both in there because that's not a particular solution. Particular means one specific unique answer. That's 2. Now plug in the initial condition. If you plug 0 in, you get e to the zeros, 1, 2. Plug 0 over here, it's negative. We actually want the negative this time. And then we finish solving, and we add 2 to both sides. And this is our solution. Now, of course, we need to figure out the domain. And the domain has 2 issues. One, it's this one, which is all reals. But you also need to look up here and say, is there any x or y value that would cause the derivative to be undefined? Because if there is, you got to break up your domain there. Any place that's not continuous or differentiable. It's a single open interval. There's no issues there. There's no issues here. So the domain is all reals. Negative infinity, positive infinity. If you don't state the domain, you lose this last point. Just count on it. You got to put the domain for the solution of a differential equation. So that was number 5. Hopefully you guys are getting pretty good with problems like that. I'd say more modern AP for response questions involving differential equations are a little less boring than that. They might involve like a word problem. So some people kind of get fooled by that. They don't realize that there's some easy big points to be earned. So just try and keep your eyes open for that. Here's a classic related rates problem. It's probably like the 3rd or 4th time you've done it. Lighthouse Rock. Lighthouse Rock. Okay, ship A is traveling due west. So it's traveling this way. So usually with related rates or things changing, I like to draw arrows to show the direction the things they're doing towards the Lighthouse Rock at a speed of 15 kilometers per hour. So I draw a picture. They already have a picture. I'm going to add a lot of stuff to it. Ship B is traveling due north away from Lighthouse Rock at a speed of 10 kilometers per hour. Let x be the distance between ship A and Lighthouse Rock at time t. Y be the distance between ship B and Lighthouse Rock at time t. Find the distance in kilometers between ship A and ship B when x equals 4 and y equals 3. So we're trying to find this distance. We call it z. I don't think I call it little d because we might have some other little d's for derivatives and stuff, and that might get confusing. But I don't know. We could just use capital D. It's up to you. Or z. Now, the underlying relationship here between all these sides is it's a right triangle's Pythagorean theorem. So we can use that to find the distance between them at when x equals 4, y equals 3. So it's 16 plus 9, 25. Square root of both sides, plus or minus, but we're only going to go with positive since it's the length distance between the two things. The units are kilometers. All right. Now, that didn't involve any calculus. That's all geometry, algebra. But this might help us for the calculus. First of all, we might need that. Also, this initial relationship between all the different variables in here might help us for our related rates. B, find the rate of change in kilometers per hour of the distance between the two ships. So we're looking for dd dt when x equals 4, y equals 3. So to find the derivative of the rate of change there, now these rates that they gave you, those must be rates of change of derivatives of things. So this one right here, this is dx dt. Now you got to decide, is it positive or negative? has nothing to do with the direction. It has to do with, is x getting bigger or smaller? X is getting smaller, so it's negative. This is, as ship B moves away 10 kilometers per hour, y also changes by 10 kilometers per hour, and it is positive because it's y is getting bigger. Do we expect D to be getting bigger or smaller? Well, this one, if they're both going out, it's getting bigger. If they're both coming in, it's getting smaller. One's coming in, one's going out, but the one coming in is coming in faster than one going out. So I kind of think it's going to be negative. It's always good to kind of have an idea. A lot of times it's even more obvious than this one, whether it should be positive or negative. That way you'll catch a mistake, forgetting negative or something. Now we need a relationship between D and all of these guys. Now, what we can do is before we take the derivative, any constants we can plug in. So can we plug x equals 4 and y equals 3 before we take a derivative? If we can, really simplifies the derivative. We can't. Those are changing. Those are just the values at a certain time. But in general, x is changing, y is changing, d is changing. So we're going to take the derivative implicitly. So you take the outer derivative and then the inner derivative with respect to time. So it's a chain rule issue implicitly. So we do that. Now, the point breakdown is 1, 4, 4. So we got 1 point for part A. And just having written this relationship down is worth a point. Having taken the derivative implicitly correctly is worth 2 points. And now we want to find dt. So this is where the 5 comes in. And we have x is 4 and dx dt was negative 15. You got to put the negative. Plus 2 times y is 3. dy dt is positive 10. So whenever I put rates in, whenever I draw them, label them, write them down, put them in, I always purposely put a plus or minus in front of them just to make sure I don't miss that. It's an easy mistake to miss. So now we can solve for this. So you'll notice I didn't try and get d capital D dt by itself before this. Just start plugging stuff in. It's a lot easier when there's numbers. So 60, negative 120, plus 60. So it's going to be negative 60. And that's going to be negative 6. And the units are, D is in kilometers, right? Distance. And time is in hours. So let's put the units. And it came out negative like we expected it would. C says, let theta be an angle, as shown in the figure. Find the rate change of theta in radians per hour when x equals 4, y equals 3. So we're looking for d theta dt when x equals 4, y equals 3. Now, do we expect it to be positive or negative? So ship A is coming in and ship B is going out. That angle is definitely getting bigger and bigger and bigger. So we should get a positive answer. Now we need a relationship between theta and x, y, and or d. Now I personally, you could use any of those. Basic trick, sine, cosine, tangent. It's up to you. I would like to stay away from d, just in case I didn't find it yet, just in case I found it and it was wrong, just in case I found it and it was just ugly, even if it was right. Same thing for d capital D dt. I'd like to not have to rely on those answers, because if I got stuck, or if I got them wrong, or if I got them right and they're just ugly. So I'd rather just work with the original information as much as possible. They're nice answers. I know they're right. So I'm going to do tangent of theta equals opposite over hypotenuse. So that's going to be my relationship. That's where the point, whichever one you decide to go with. We're going to take the derivative of it implicitly. Derivative secant is, or derivative tangent secant squared, but you need a d theta dt, which hopefully would bother you if you didn't have it, because that's what we're trying to find. And over here is going to be quotient rule, low d high minus high d low all over low squared. So this right here is worth 2 points, implicit differentiation correctly. Now we just got to solve for this. Now secant is 1 over cosine, right? And cosine is adjacent over hypotenuse. So going back to the original triangle, adjacent to that angle is 4, and the hypotenuse is 5, and then it gets squared. Over here, x is 4, dy dt was positive 10, minus y was 3, dx dt was negative 15. And so if you mess this up, if you forgot the negative on this, you'd get positive you get a negative answer, which would bother you because you predicted it was going to be positive, right? Over x squared. So d theta dt equals 40 plus 45 over 16 times, this is going to be 16 over 25, right? So we're going to multiply by 16 over 25 to get that to cancel out. 16s cancel, get 85 over 25. You could leave like that or simplify it, 17 over 5 radians per hour, and came out positive like we thought it would. That's the last point. So, oldie but a goodie. Little related rates practice there. So, hope that kind of jogged your memory a little more, and you're all the more ready for your AP test.